vaccine from other company like Pfizer, AstraZeneca, and then there's also Nopopak from China also. Yeah, so like 4 or 5 brands of vaccines. Government tried to use different types of vaccine for more than 180 million people by the end of this year.
Okay, it's time. 3 minutes more.
Another 3 minutes. Still wait.
Wait.
Maybe we can start early in the opening. Oh, Dr. Jun.
Yeah.
Is it okay if we go past from 2 hours? Like
2 hours ahead.
Yeah, if we have like a longer questions and answer, perhaps it's just still
yes.
estimations.
It's okay.
So okay.
Yeah.
So we got permissions for longer question and answer. All right. Another 2 minutes, maybe in 1 minute we can start. Pak Edi.
Eddie, yeah.
Yes, I'm here.
Yeah,
we are go for live.
Facebook?
Yeah. Yes, already live on Facebook and YouTube.
Okay, already live on Facebook and YouTube.
Yes.
Thank you, Pak Eddie.
You are welcome.
Okay, I think we are ready. Okay, I think we can start earlier. Rico, we can start?
Yeah, okay. Let's start.
Okay, let's start. Ladies and gentlemen, Director Research Center for Physics, Indonesian Institute of Sciences, Dr. Rika Yudianti, respectable speakers, Dr. Jun Maruyama from Osaka Research Institute of Industrial Science and Technology, ORIS, Dr. Wahyu Bambang Widayatno from Research Center for Physics, LIPI, Mrs. Fredina Destyorini, MT from Research Center for Physics, LIPI, Dr. Andri Hardiansyah from Research Center for Physics, LIPI, and all super participants. Good afternoon and welcome to webinar on functional carbon materials for electrochemical energy devices. My name is Andi Suhandi. I am a research program coordinator in Research Center for Physics. I will guide this webinar until closing time. This webinar is organized by Low Dimensional Functional Material Research Group, Research Center for Physics, LIPI, as part of our JSPS collaborations with Osaka University and Osaka Research Institute of Industrial Science and Technology, ORIS, Japan. This special event is part of our knowledge sharing program on Colloquium of Physics, which usually held twice a month, every other Tuesday morning. So this is a special event on Wednesday afternoon. So let me first introduce our agenda for today's webinar. First, it will be started with opening remarks by Director of Research Center for Physics, then followed by photo sessions. Next, the main event is the presentations and discussions. We will divide it into two sessions, session 1 and session 2, because we have 4 speakers. And last, the webinar will be closed by myself as an MC. Okay, ladies and gentlemen, we would like to start our webinar with the opening remarks from Director Research Center for Physics. Please welcome Dr. Rika Yudianti. Dr. Rika, time is yours.
Terima kasih, Pak Andi. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Good afternoon, ladies and gentlemen, and my distinguished guest, invited speaker, Dr. Jun Maruyama from Osaka Research of Industrial Science and Technology, Osaka, and all Indonesian speakers from Research Center for Physics. Thank you for all your willingness to join with in this seminar, and all audience to join in our seminar. In this seminar, we are a topic about the carbonaceous material which have potential application for electrochemistry, the energy. So this topic is still, I think, still interest to be discussed, and progressive carbon technology in science and technology. In our research center, we have research groups named low dimension functional materials, whose the activity are related to any kind carbon material like carbon based like graphene and carbon nanotube and bio-based carbon materials. So then sometimes we use for any kind application, functional application like electrocatalyst, photocatalyst, and sensor, and some application in electrochemistry devices. And actually, we already conducted a research in carbon material since over 5 years ago. And 2019, we agreed to establish new research group named Low Dimension Functional Materials until now in 2020. And because this topic of the seminar is about the carbon material, so in this seminar, I invited Dr. Jun Maruyama, who has expertise and experience in carbon materials. So we already make a collaboration with through Professor Hiroshi Uyama under bilateral GSPS LIPI project in 2020 in porous carbon application. So I hope Dr. Jun can share us about insight and knowledge about carbon, and I hope the audience can utilize this moment to make a collaboration with our all invited speaker. So I think that's all my remark today. Hope this seminar will give us insight, knowledge, and research collaboration with our guest speakers. Again, thank you very much for this opportunity, and thank you again for your joining in this seminar. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Thank you, Dr. Rika, for your warm opening remarks. Our second agenda is the photo sessions. For the photo sessions, please turn on your video and give a big smile. Mrs. Yuyun will take our photo. She will give comment for every page she take. Mrs. Yuyun, time is yours. Mrs. Yuyun?
Okay. Please turn on the camera, the video, and give big smile. Wait. 1, 2, 3. Wait a minute. And next page. One, two, three. Thank you.
Done?
Yes, already done.
Okay, thank you, Ms. Yun. Mrs. Yun is also part of the low-dimensional functional material research group. Okay. Ladies and gentlemen, we come to our main event, which is presentations and discussions by our four respectable speakers, moderated by myself. Session 1 will be presenting Dr. Jun Maruyama and Dr. Wahyu Bambang Widayatno, and also followed by question and answer. And session 2 will be presenting Mrs. Fredina Destyorini and Dr. Andri Hardiansyah, also followed by question and answer. Participants can write down in chat box if you have questions, or you can also ask directly your questions by raising hand on the Zoom panel. Thank you. For the first speaker is our invited speaker, Dr. Jun Maruyama. Let me introduce him first by reading his brief career history. Name is Dr. Jun Maruyama. His positions as a senior research scientist, Environmental Engineering Laboratory, Research Divisions of Environmental Technology, Osaka Research Institute of Industrial Science and Technology. His education is in 1994 to 1999, PhD in Department of Energy and Hydrocarbon Chemistry, Graduate School of Engineering, Kyoto University. His employment record, 1999 to 2012, as a research scientist, Osaka Municipal Technical Research Institute, 2008-2009, visiting scientist, Department of Physics, Technische Universität München, 2012 to 2017, research senior research scientist, Osaka Municipal Technical Research Institute, 2017 to present, is as senior research scientist, Osaka Research Institute of Industrial Science and Technology. He has also several awards recorded here. 2007, Young Researcher Award of the Carbon Society of Japan. 2008, the Committee of Battery Technology Award of the Electrochemical Society of Japan. 2010, 60 Industrial Technology Award, Osaka Industrial Research Associations. 2018, Award of the Carbon Society of Japan for academic achievements. 2019, Award of Joint Research for Materials and Devices. His specialized field is development of carbon materials for electrodes in polymer electrolyte fuel cells, zinc air batteries, water electrolyzers, redox flow batteries, electric double layer capacitors, and development of porous carbon materials. That's a very outstanding achievement from Dr. Jun Maruyama. So Dr. Jun, time is yours.
Okay. Thank you very much for inviting me to this seminar. And I'm very happy to see you all. And I'm very looking forward to begin the research program based on JSPS for 2 years. Yes, before the research project, I would just like to introduce you my research topic today. This is a very great opportunity for me to introduce you about my research activities in Japan. So let me share my PowerPoint slide. Can you see PowerPoint slide? And,
Yes, we can.
Yes.
And voice volume is okay?
Okay, clear.
Okay.
I think it's a little bit low.
Volume is low. Okay, I try to increase the volume. Okay. Good. So let me start my presentation. And before going into detail, let me just briefly introduce my research institute in Japan. So I'm in Japan here, and you are in Jakarta, Indonesia here. Yeah, and yeah, you are in Southeast Asia, and I'm now in Far East Asia.
Excuse me, your
Yes.
is not. Your voice is loud enough. Your
my voice not enough. Okay.
Okay. Enough.
I think you need to closer the microphone.
Yes. Then I will do it like this.
Yes, that's better.
Okay. So, Osaka. We are in Osaka right now, and Osaka situates west of Tokyo, about 500 kilometers. And when we enlarge here, okay, something wrong?
No, it's okay.
Okay, then move on to the next slide here. And Osaka city is surrounded by Osaka Gardens area and Kyoto. And here is our largest lake in Japan called Biwa Lake. And Osaka University situates in Suita City, just very close to our institute, just 1 hour north from here. And our institute situates just east of Osaka Castle, like this. And Osaka Castle, we can see very closely from our institute.
Oh, it's great.
Yeah. And our institute was founded in 1916. So we have history over 100 years. And our research activities mainly focused on chemistry. And especially we are doing research and development on carbon materials more than 60 years. So we have a lot of knowledge and skills on carbon materials. And the researches on carbon material in Osaka Research Institute divided in 6 categories, like here. We are doing air electrode research and lithium battery research. Fuel cell catalysts are also developed. And electric double layer capacitor, water electrolysis catalyst, and electrode materials for redox flow batteries. These applications are all belonging to electrochemistry. So this is based on my knowledge gained from PhD research, and I'm trying to combine carbon material science knowledge in Osaka Research Institute and my knowledge from PhD. I would like to introduce these topics just briefly, and maybe we have enough time later in 2 years after the project begins. So today I'm trying to introduce you as much as possible, but it's limited. So I just tried to introduce you about fuel cell catalyst. Before going to the research topic, I just mentioned the carbon material I'm especially interested in. I'm especially interested in carbon materials doped with metal. And relationship between carbon and metal is very strong. We can see iron carbide or other metal carbides and metal carbon composite. This is insertion materials. And even pure graphite contains metals as impurities. Metals are very difficult to remove from the graphite. And especially metal inclusion like this, metals coordinated by nitrogen, and this structure is included in graphene layers. These materials are my main research topics. And actually, these materials is easy to be synthesized. One of the raw material is iron ferrocyanide, and just sublimation and deposition and pyrolysis can make these two-dimensional layer lattice-like structure containing iron and nitrogen. This is TEM image showing iron particles are aligned or in a regular way. And the method is also simple, just introducing the substrate and the raw material iron ferrocyanide in a crucible like this, and heat treated at typically 800 degrees Celsius in argon an inert atmosphere. And then if we examine the nitrogen physical state by nitrogen KH X-ray at near edge structure, we can elucidate the two-dimensional lattice-like structure. Actually, this experiment shows that the iron are connected by these one Linsen bridges. And X-ray absorption spectra also shows us the information about the orientation of layer, if it is perpendicular to the surface or horizontal to the surface. Actually, this is horizontal, and we can also get some catalytic activities on the surface, and the presence of nitrogen and iron was also observed. And this is iron or metal inclusion into the carbon, but it's not sufficient to function as a catalyst. If the active site is included in carbon and totally blocked from the access from outside of the surface, it is not functioning as a catalyst site. We have to make pores like this to be accessible. So the pore development is important to make an active catalyst. So a pore development and metal inclusion are my research interest in 20 years in Osaka. So from now, I briefly introduce the details of my research topics. First, I would like to tell you about a carbonaceous fuel cell catalyst. Fuel cell catalyst is important to make high performance fuel cell, and I'm interested in polymer electrolyte type fuel cell. One of the trial for making a non-noble metal catalyst is done by using hemoglobin containing iron heme a compound as an oxygen binding site. If we change the carbonization conditions, different types of irons are included in carbon materials. That leads to enhancement of reactivity. And if we change the heat treatment conditions, we can get iron nitrogen structure, different iron nitrogen structure observed by X-ray absorption fine spectroscopy. These catalysts have different stabilities. These are very preliminary, but this is my almost first step into carbon research. After that, I tried to make highly porous carbonized hemoglobin by using ammonium activation. It is successful, but not sufficient enough. I use these iron nitrogen activated active site to make another catalyst for zinc-wire batteries. Zinc-wire batteries have zinc anode and air cathode. And I'm trying to make air cathode using carbon materials. And I use highly oriented pyrolytic graphite as a model carbon electrode. And I formed this active site on graphite. And I also loaded manganese oxide. And I also make a pit-like three-dimensional structure using catalytic activity of cobalt oxide. These are the examined surfaces. I examined the various surfaces for oxygen evolution reaction and oxygen reduction reaction activities. This is a photo of X-ray synchrotron facilities, and I'm using this facility very often to examine the active site, including iron and nitrogen. And this is results for a catalyst to oxygen reduction activities and oxygen evolution activities. One of the most outstanding result here is the finding that these surfaces can have very active from the very low overpotentials. And these very low overpotentials can be achieved considering these reaction mechanisms involving two kinds of active site. And this is an intuitive image showing the importance of step and terrace site. Step, terrace, and these lights are indicating the reaction progress. And I also using carbon materials as a catalyst in redox flow batteries. Redox batteries is very advantageous device for storing in electrochemical way from the energy from renewable sources. And the redox flow batteries can charge and discharge based on these chemical reactions, vanadium redox reactions. I'm using these carbon fiber surfaces. This is modified surfaces, and I observed the significant enhancement of the performance of the vanadium redox flow batteries. These modifications are made by surface etching by cobalt species. And I found that these active site, active for oxygen reduction and oxygen revolution, also enhances redox reactions of vanadium species based on the reaction mechanism shown here. And also, this is an intuitive image for showing the enhancement of reactions at the active site containing titanium or iron. sorry, when can I talk? Until when?
You can have like half an hour, maybe in 10 minutes or 15 minutes.
Okay, in 10 minutes, okay. Then I can introduce briefly about hydrogen evolution also.
Okay, thank you.
Mhm. The concept for making catalyst is actually similar. Hydrogen evolution reaction can be catalyzed cobalt containing a catalyst. So I used cobalt cyanin as raw material, and by sublimation, deposition, and pyrolysis of cobalt cyanin, I could get these agglomerate-like electron conductive high surface area material that is active for hydrogen evolution. This is a result obtained from X-ray absorption fine spectra. And this image shows the components of cobalt species. The content was changed according to the conditions of heat treatment, and optimized heat treatment conditions can produce a very active hydrogen evolution catalyst containing cobalt. This is also an intuitive image for cobalt catalyst to make hydrogen evolution. And we also introduce another topics about carbonaceous materials. These species may be already published in collaborative work with Professor Hiroshi Uyama, and we are doing collaborative work for a long time. And I'm also very interested in very special shape materials. These materials was once applied to electric double layer capacitor. That shows one of promising performance. These are recent results from collaborative work with Professor Uyama using biomass raw materials. We used chestnut or some kind of fruit, and we can make very highly porous carbon materials that can be used as an electrode of electric double layer capacitor. If we use polystyrene nanoparticles as a pore template, I can make a very three-dimensionally ordered porous carbon materials. And these walls can be graphitized easily, and these walls also can have ability to lithium storage. And this technique can be applied to make another porous materials that have helical alignment of pores like this. And this helicity can make optical activity. Helicity can impart optical activity to the carbon material itself. And I'm now trying to make these some special properties for some application. I'm searching the application field right now. This is helical alignment of the pores. This is right-hand helix and left-hand helix. The helix pitch are different from the orientation of rotation of helix. This is interesting, but doesn't have application field right now. And I also make some sophisticated carbon materials with very ordered, three-dimensionally ordered structure. Also, this is have metals included through nitrogen. And also, I'm trying to find application field of these materials right now. So this is a summary of my talk today. I just briefly introduce you about these 6 areas. I'm doing researches based on carbon materials and electrochemistry. I'm trying to get synergetic effect of these 2 fields. And I hope these studies can make some fruitful results like this. Yes, and I'm also looking forward to collaborating with you next 2 years and get some fruitful results also. So thank you very much for kind listening to my talk. Thank you very much.
Thank you, Dr. Jun, for your wide area of research presentations. Ladies and gentlemen, you can write down your questions in the chat box, or you can ask directly later on. If not for technical questions, you can also ask questions regarding future collaborations with Dr. Jun. That's also part of this program. I think we enhance collaborations. Okay, for the second presentations will be Dr. Wahyu Bambang Widayatno. Dr. Yes, thank you. I will read briefly about Dr. Wahyu Bambang. Name is Wahyu Bambang Widayatno. His positions as senior research scientist in High Resistant Material Laboratory, Research Center for Physics, Indonesian Institute of Sciences. His last education is in 2013 to 2016. He's Doctor of Engineering in Safety Science and Technology, Graduate School of Science and Technology, Hirosaki University, Japan. And his career as a researcher starting from 2006 as a research scientist in the Research Center for Physics, Indonesian Institute of Sciences. His research interest is in porous material, waste to carbon conversions, and material polarizations. Dr. Wahyu Bambang, time is yours.
Okay, thank you. Thank you, Mr. Andi, for the introduction. Is my voice clear enough?
Not really. You can start your
Okay, is my voice
share.
clear enough?
Your voice is okay, but you can start your sharing your screen. Hello. Dr. Wahyu.
Hello.
Yes.
Okay. Okay. Thank you, Mr. Andi, for the introduction. Thank you very much, Dr. Jun, Dr. Rike, for the opportunity given to me to present my work in the last year about synthesis of textured porous carbon from industrial coffee waste using novel low temperature activation method for energy storage application. Is also funded by ITSF program, and try to present this work. First, we talk about coffee, because in my title is we talk about people in the world like coffee, and also most of Indonesian the coffee in Indonesia has become
Mr. Wahyu.
lifestyle. So we can see here the graph from, yes. Hello.
Yeah, your voice is run off.
Hello, check.
Yeah, your voice is run off.
Better to switch off your screen to make the signal better.
Video, yes.
Okay. So my is already clear
Yes, clear.
enough.
Yes, yes. Please continue.
Yes, just continue, please. Dr. Wahyu.
Hello, check.
Yeah.
Hello. Okay. Can I continue?
Yes, please.
Okay. Sorry. The connection in my room is not so stable, so I'm sorry for this kind of problem. So if we see the consumption of coffee in Indonesia, usually especially in Indonesia, we can see here in the black lines here, we can see here from year to year there is some significant increase for the coffee consumption. So the increasing coffee consumption will lead to the, sorry, I cannot hear.
Yes, please.
I cannot move my slide. Sorry. Let me stop share.
Can I share your slide?
Okay, okay. I will send to you. I will send to you.
No, no,
because,
I have.
this
I
slide,
think. Is it new?
no, yeah. I have already add some data. I will send it to you
Okay.
now.
Or we can swap.
Yeah. I think better if we can swap the speaker because
Yes,
I still
I
have
think
some
we can
problem
swap
with the
first.
connection here.
Miss
Sorry.
Tina, are you ready?
Okay. Okay, Pak.
Okay, yeah, I think it's better if you're ready. You can start sharing screen.
Okay. Can you see my slide?
Yes, good.
Okay.
Your voice is clear. You can start, please.
Clear? Okay, I can start. Okay, thank you, Mr. Andi.
But I haven't introduced you.
Oh, okay, please.
I think I need to introduce you first. It's okay, the slide. Okay, our current speaker is Mrs. Fredina Destyorini, MT. His educational background, BSc in Physics, Physical Science from Department of Physics, Airlangga University, Surabaya. His master degree is from Material Engineering from Department of Metallurgy and Material Engineering, University of Indonesia. And currently she is taking JSPS Ronpaku PhD program in Osaka University, Japan, which her research title is in fabrications of graphitic carbon paper from coconut coir for gas diffusion layer of PEM fuel cells. Her research interest is in graphitic carbon materials derived from biomass and material for energy like fuel cells, battery, and supercapacitors. Processing and characterizations of carbon composites, development of carbon paper processing as gas diffusion layer of proton exchange membrane fuel cell from natural fibers. Okay, that's the Mrs. Fredina Destyorini. She is also member of the Low Dimensional Functional Material Research Group in Research Center for Physics. Mrs. Fredina, time is yours.
Okay, thank you. I ask permission to turn off my video. Mr. Andi, is okay?
Yes.
Okay. Okay, good afternoon, everybody. I am Fredina from Research Center for Physics. See you again in our second webinar about carbon. And today I will share our experience about a conductive and porous carbon composite paper from coconut waste as gas diffusion layer for polymer electrolyte membrane fuel cell, or we call it with PEMFC. and more detailed information than my previous presentation, and it will be focused on carbon for fuel cell application. Okay, let's start with this. This is the outline today. Consists of introduction and fabrication process of coconut coir carbon composite paper, or we will call it with CCP, and then application of CCP as gas diffusion layer, or GDL, of PMFC, and I will share about our ongoing research in our lab. Okay, maybe some of participants in here have seen this slide in our previous webinar. I just want to deliver to you that the following things are the background or our reason why we focus on carbon material from biomass waste. Most of our energy comes from fossil fuel, and burning the fuel causes environmental pollution. And we know that fossil fuel is a non-renewable resources, so it has a tendency availability to run out. Therefore, this global problem, they are the depletion of fossil energy, global warming, increasing environmental pollution, and waste disposal have become the focus of the international community. In the face of global energy and environmental problems are getting worse, the development and utilization of new and renewable energy sources have become the common choice for countries around the world to ensure energy security and achieve sustainable development. Electrochemical energy devices is one option of this new and renewable energy source. They are fuel cell, lithium-ion battery, and supercapacitor are the most typical and popular. Carbon material have been the ideal candidate material for this device because their diverse structure, rich surface area, strong controllability, and good chemical stability. Porous carbon material with high surface area and good stability have been widely used as electrode material. The use of biomass waste like coconut waste as carbon precursor also is a great approach in waste management and pollution control strategy. And the following advantages of biomass waste as carbon precursor, they are highly porous structure, abundant, and renewable. We utilize coconut coir, which is an agricultural waste product generated in large quantities in Indonesia, to generate a value-added product. Biomass-based material generally contain lignocellulose compound like hemicellulose, cellulose, and lignin that can degrade at different temperature and produce a carbon material as its residue. With some treatment, biomass waste, including the coconut coir, could convert to porous and conductive carbon material that have attracted great interest for electrochemical energy devices. And we will focus on the application of carbon in fuel cell application. And this is our research overview to convert the coconut waste into a value-added product and apply it as one component in fuel cell stack. For the material, we use coconut waste, especially the coconut coir that are currently still underutilized as compared to other waste. Coconut coir is a byproduct of coconut plantation that extracted from fibrous coating of coconut fruit. Moreover, the process, we use some process to transform this waste into value-added product. At first, we carbonize the coconut coir into conductive carbon material and mix this carbon material with some polymer binder, followed by casting process on mold to produce a product of porous and conductive carbon composite paper with thickness around 0.3 to 0.6 millimeter. To be applied as GDL of PMFC, the paper should have the following properties: conductive, good mechanical properties, hydrophobic, and porous. Finally, for the application, we insert the paper in the stack of fuel cell, replacing the commercial carbon paper as GDL, and test the performance in the PMFC system. Carbon material that used in commercial GDL are generally produced from fossil fuel. We know that fossil fuel is non-renewable resources. which raises concern about sustainability. By using coconut waste, it can be resolved this sustainability issue due to the renewable nature of coconut. The goal of our research is to produce carbon composite paper that is able to function as GDL of PMFC and has the following properties. This one. In addition, we use commercial carbon paper that have established in use of GDL in PMFC, such as Torre carbon paper, for comparing the properties of our sample. If the properties of our sample are similar or close to the Torre carbon paper's properties, so it indicates that our sample are ready to apply as GDL in PMFC system. We have to make sure this value first before applying process in stack of PMFC. Okay, why we choose coconut as a raw material? This is the reason. As a tropical country, Indonesia is the world top producer of coconut, followed by Philippines and India at second and third position respectively. Indonesian coconut plantation cover 3.5 million hectares and 17.7 million tons of coconut are annually produced. The highest contributor is in Riau in Sumatra Island, followed by Java Island and Sulawesi Island. However, coconut production generates a large amount of agricultural waste. Coconut production account for about 35% of the production of coconut fruit each year. Poor management and improper disposal of coconut waste generate pollution that is socially and environmentally problematic. To ensure that coconut production does not adversely affect the environment, efforts should be made to convert the abundant waste into value-added product. Coconut coir is extracted from the outer coat of the coconut fruit, as shown in the interior structure of coconut. This fibrous material found between outer coat and hard shell of coconut. Coconut coir is a lignocellulosic material that is primarily composed of cellulose, lignin, and hemicellulose, with each composition. And this lignocellulose compound degrades at different temperatures through carbonization in oxygen-limited or oxygen-free environment to produce carbon-rich charcoal as residue. And this is the morphology of the coconut coir carbon observed by SEM. We can see the original coconut coir structure, namely fiber, with a several parallel hollow tube close to each other. Using the greater magnification, we also observe the pore with a diameter around 1 micrometer spread in the fiber cell wall. Owing to its chemical composition and unique morphology, coconut coir waste can be recycled or utilized as a renewable and relatively inexpensive carbon precursor, even a graphite precursor, with additional treatment. With these following advantages, abundant, porous, renewable, and so on, and we have checked the electrical conductivity of this carbon is around 14 to 17 Siemens per meter. Using biomass waste as a raw material of carbon paper production could resolve the sustainability, economy, availability, and waste management problem. Okay, this slide is talk about fuel cell. Fuel cell, you know that fuel cell is type of environmental friendly electrochemical energy conversion device that can directly convert chemical energy into electric energy on the basis of redox reaction without the combustion process. The oxidation of fuel, in this case, is H2 oxidation occur in the anode and oxygen reduction reaction, or ORR, at the cathode. PM fuel cell pose a multi-layer architecture and typically consists of anode and cathode, flow field plate, and membrane electron assembly, or MEA. Several papers report the application of biomass-based carbon as catalyst layer and gas diffusion layer due to its porous structure, low cost, and relatively easy preparation. And gas diffusion layer perform the following essential function to transport reactant electricity and heat, as well as providing structural support assembly. And this is the catalyst layer. I just want to focus in the GDL. Biomass carbon has a potential to utilize as gas diffusion layer, replacing the commercial carbon paper due to its porous and conductive. In order to perform the GDL function, GDL should have appropriate porosity, good electrical conductivity, proper wetting characteristic, and enough strength. They are the primary requirement that must be posed by material to be applied as GDL of fuel cell. Okay, for the detail of experimental method, we start to prepare the carbon material from coconut coir. Carbon material was produced in two different forms, carbon fiber and carbon powder. Both carbon were obtained from coconut coir by carbonization and pyrolysis. For the carbonization process, the coconut coir was heated at around 500 degrees Celsius under a nitrogen atmosphere, followed by pyrolyzed at higher temperature, up to 1,300 degrees Celsius under nitrogen temperature to obtain carbon material with high carbon content and conductive. For the final product, carbon powder was obtained by grinding and then mass sieving to size about 75 micrometer. And for the carbon fiber process, the coconut coir was first cut to length of about 2 millimeter before being subjected to carbonization and pyrolysis. And then for a manufacturing step of carbon composite paper, the CCP were prepared by mixing the carbon material with polymer binder and mixed to form a slurry. The slurry then cased on molded and then dry to form a paper. In this work, two types of CCP were made with different shape of carbon. We can see the composition detail in this table. Okay, to improve the hydrophobic property, both type of CCP were treated by dipping in PTFE suspension, the hydrophobic agent, and drying this, and followed by heat treated at around 350 degrees Celsius in air atmosphere, and then apply the CCP in the single cell of fuel cell to check the performance in the PMFC system. This instrument is available in our laboratory. Okay, this is the microscopic surface and cross-section morphology of CCP1 and CCP2 and the commercial carbon paper for a comparison. This is the commercial carbon paper. We can see that the surface of CCP1 with carbon material in powder shape appear smooth than CCP2, and in the CCP2 it shows the discontinuous fiber-like shape with a larger dimension and higher aspect ratio, split randomly throughout this composite surface, and the pore formed by the internal space between the carbon fiber. And for the commercial carbon paper, it can be seen that commercial carbon paper is composed of solid and non-porous carbon fiber with a finer diameter and higher aspect ratio compared with CCP2, and the pore are formed by internal space between the carbon fiber as in CCP. And this is the physical properties of our composite compared to commercial carbon paper. For the porosity, we can get the similar value, and then the contact angle or hydrophobicity properties is good enough, but we have a problem in the electrical conductivity is still lower than the commercial carbon paper. And for this, SEM is to check the distribution of PTFE particle in our composite. We can see that with the red area is represent the floor element from the PTFE, we can see that the PTFE can penetrate inside the composite, similar with the commercial carbon paper. And if we check the hydrophobicity properties with the contact angle measurement, we can see that PTFE give a significant effect to improve the hydrophobicity. This is the untreated PTFE, and this is the treated PTFE compared to the commercial carbon paper. The hydrophobic properties is similar to commercial carbon paper. And we also observe the variation content of PTFE on our CCP properties. We use 3 different PTFE content. They are 10%, 20, and 30. And if we check the properties, we can get 10% PTFE is the optimum content of PTFE that produce good properties in our CCP. This is the porosity. We know that PTFE can block the porosity of our composite, but with 10 PTFE, the porosity is still high, and it's good, I think, compared to the commercial carbon paper. And
Fredina, 5 minutes.
Yes, for the true plant conductivity, the 10% is high enough. Okay, this is the fuel cell performance test of CCP. As I mentioned before, that we have this instrument to check the performance of GDL in PEMFC stack. We get an IV curve, and we can summarize that our composite have a current density around 232 milliampere per centimeter square. It's close to the commercial carbon paper. So we can summarize that our composite is successful to apply SGDI in PEMFC. Okay, this is our ongoing research. As I mentioned before, that our research, our properties in CCP is still have low conductivity. So we conduct some treatment to improve the electrical conductivity using catalytic graphitization to convert the amorphous carbon into graphitic structure. And this is our publication. We are successful to convert the structure, amorphous structure, to graphitic structure and improve the electrical conductivity. We use a nickel catalyst to reduce the temperature of graphitization. And we can see that from the TEM, we have a very good crystallinity, I think. And our sample is ready to apply in the electrochemical devices, including in anode lithium battery, GDL in fuel cell, and also supercapacitor. And also we have collaboration research with Universitas Pertamina and Pertamina Company to make a FANC electrocatalyst for ORR reaction. And
2 minutes.
The result is, yes, it's good enough. I think we have the ion set potential is in the area with other previous research around the world in KOH condition, also in the acid condition. Okay, I think it's enough, Mr. Andi. Thank you for the time.
Thank you, Ms. Dina. Ladies and gentlemen, now we can open for questions and answer.
Come.
For about maybe 10 to 12 minutes. So first maybe is asked by Muhammad. What is his? You can Muhammad Fasa, ya. Muhammad Fasa Nur. You can ask questions directly because you said you want to ask questions. Mr. Muhammad Fasa? If not, there's questions for Dr. Maruyama himself from Mrs. Yun. Dr. Maruyama? Dr. Jun?
Yes.
This is the questions.
Yes.
Is there any special treatment improve
for
the
me.
porosity of FENC electrocatalyst, and what type of pore, micropore or mesopore or hierarchical pore structure that is the best for ORR applications?
Yes. Hierarchical pore structure is desirable for catalyst, as catalyst for PFC. The increase of pores for development leads to the increase of activity. As long as the electron conductivity loss was minimized. Of course, micropore develops, electron conductivity decreases. So we have to be careful about electron conductivity when we're doing development of pores. And regarding, yes, that's my answer.
Okay.
Is it okay?
Is Yun? You want to ask more questions? Is it enough?
Can I ask?
Yes,
questions?
yes. I think there is also questions from Dr. Jun to Mrs. Fredina, right?
Yes,
Right.
yes, I get question
Yes.
from Dr.
Does
Jun.
coconut coir contains metals?
Okay, thank you for the question, Dr. Jun. From the XRD observation, if we carbonize the coconut coir under 900 degrees Celsius, we can find a calcium element in our coconut carbon. But when we increase the temperature up to 1,300 degrees Celsius, we cannot find the calcium element in our carbon. So we use the temperature now to apply our sample is around 1,200 degrees Celsius, Dr. Jun.
Okay, you mean potassium or calcium?
Potassium, K.
K.
Yes.
Okay, calcium is not contained in coconut core? No, potassium is the main mineral in coconut core. Potassium.
Yes.
Yes. Okay, it's interesting. Thank you.
Okay, maybe I can ask a question for you, Dr. Jun. Mr. Andi, can I ask question? Because
yes, please.
His presentation is so very interested for me. Dr. Jun, my sample, I want to apply my sample in fuel cell and also supercapacitor application. And I checked the performance of my sample as supercapacitor with CV, CV test.
Yeah.
For the electrolyte in CV, which one is better in acid or in alkaline condition? Because when I use 6 molar KOH in CV test, we cannot get the good data. Maybe you have an situation in experimental method.
Yeah, for CV measurement, as a fundamental investigation, maybe you can use both acidic or alkaline electrolytes. Yeah. Maybe fundamental data does not so influenced by the choice of the electrolyte. You can use sulfuric acid, you can use potassium hydroxide. Yes. You can
How
use,
about the effect of the concentration of both of solution?
Yeah, maybe high concentration of potassium hydroxide would be not so good regarding the viscosity. Maybe more dilute solution of potassium hydroxide, like 1 molar or 0.1 molar.
Okay.
Yeah, good for fundamental research, I guess.
Okay, thank you for your answer. Okay, Mr. Andi, any other questions?
There is questions to Mrs. Fredina. How about the mechanical properties of the obtained GDL for PMFC, such as bending, pressing, or tensile? And how about the durability of the GDL, like how many cycles or how many operating hours for their best performance? This was by Dr. Indriyati, I think, in Bandung.
Indriyati from Bandung. Thank you for the question,
I think
Mbak Indri. Okay, thank you. For the mechanical properties of our GDL from coconut coir, we have a test with tensile only. And yes, when we use polymer binder with the PEG, polyethylene glycol, and EPA, ethylene phenyl alcohol, the mechanical properties is not so good. I mean, the tensile strength compared with the commercial carbon paper is still lower than the commercial, but we can apply it as GDL in PMFC system and produce a good data, I think. But in the future experiment, we will change the polymer with the more strength polymer like resin, I think, or hydrophobic polymer like PTFE or PVDF polymer. And for the durability, yes, until now we haven't conducted the durability experiment in our performance of USL to check the IV curve in the many cycle, because you know that this system in our laboratory is so sensitive. So we until now we haven't conducted that experiment for the durability test. I think for next experiment.
So there is another questions for you, Mrs. Fredina.
Okay.
From Ibu Anna Sukmawati. When using other biomass or fruit cells, not coconut coir, does carbonaceous using 500 degrees C to get carbon? Can you read it?
Yeah.
The chat, Miss Fredina.
For me, you mean?
It's to Mrs.
For
Fredina.
me.
Okay.
Okay, I will answer. Maybe I can answer. For biomass based material, most of them is composed of lignocellulose compound like lignin, cellulose, and hemicellulose, and that compound will degrade up to 500 degrees Celsius. And so carbonize that biomass based material up to 500 degrees Celsius, which degrade that compound and produce a carbon or charcoal as residue. Yes, I think that answer maybe can answer Miss Anna's question.
Okay. Next questions is to Dr. Jun from our staff here, Dr. Saspan Arman. Thank you for the nice presentations, Dr. Maruyama. Based on your presentations, your use FeN4 and cobalt N4 as the active site for the catalyst. Could you explain the fundamental different characteristic between both of them?
Okay. The fundamental difference between iron and cobalt is actually the redox potential.
Redox potential.
Yeah. And actually iron is good for oxygen reduction and oxygen evolution. And cobalt is good for hydrogen evolution. So these metal species is very different type of activity. Yes. So we have to choose the correct metal species for the desired catalytic reactions. Is it okay? Can I answer?
Thank you for the answer, Dr. Maruyama. If I can ask you again, and
last question, please.
Yeah, around the cobalt or iron, you have a nitrogen, 4 nitrogen.
Right.
And then how is it? Can you find another structure which is you don't have 4 nitrogen? So how different? I mean, so we can see the rule of nitrogen to support the cobalt or iron. Thank you.
Yeah. In my experiment, I found that iron and 2 nitrogen structure. Yeah, that FeN2 structure was found on the edge-oriented active site, and FeN4 is oriented on the terrace, a flat surface. So there are different types of active site.
Oh, I see. Okay. Thank you, Dr. Maruyama.
Thank you, Dr. Saspan. Ladies and gentlemen, because we have very limited time, I think our sessions for the first sessions is over. We will continue with our second sessions. We will be presenting Dr. Wahyu Bambang again. I hope his connections is fine. Dr. Wahyu Bambang, please.
Okay, I'm ready now.
Yes.
Okay, thank you, Pak Andi, for the introduction. I'm sorry for the previous problem in my connection. So I would like to continue my presentation. So after this one, after we see the the increasing trend of domestic coffee consumption in Indonesia. Excuse me. Okay. We can see here with the increasing trend of coffee consumption, of course the waste also will be increased. So in Indonesia we have so many biomass waste, coffee waste, coconut coil waste, palm tree waste, and many waste from biomass waste. So the problem is how we can deal with this kind of waste. So one of the simple approach is to convert this kind of biomass waste into the carbon. So if we can convert the biomass waste into the carbon, and also we can add some functionalities. Of course, we can add some give some added value to the waste material. So we can also get some benefit from this kind of waste. So in Indonesia, the trend of activated carbon demand from year to year, from 2014 to about 2018, increased to some extent. So this increasing trend of imported activated carbon reflect the increase of domestic demand for any kind of utilization. So activated carbon itself in Indonesia can be used as material for energy storage, can also be used for catalyst, like previously presented by Dr. Maruyama, and also can be used for water purification. For this kind of application, we have to modify the surface area of the carbon, and also we have to adjust in which application, for typical application, usually needs specific application. For example, it will need more macropore structure, but it will need more mesopore structure. Try to use this kind of porous carbon for energy storage application. As you also know, there is one kind of energy storage device, which is lithium-ion battery, and also we know also one of another energy storage device, which is electrical double-layer capacitor. And in here we want to combine this kind of two energy storage device into one energy storage device, which is lithium-ion capacitor. So in here we will use the lithium carbon and activated carbon as an electrode in this kind of device. So when we combine this kind of two device, we hope to get higher energy density and higher power density compared with the previous one. So the challenge of the porous carbon itself, because usually when we synthesize, when we modify the porous carbon, we will start with the carbonization, and after that we use activation to increase the surface area and pore characteristic of the carbon. However, if we can see in detail, for the activation itself, it will use either chemical activation or physical activation. For chemical activation, it will use abundant amount of chemical compounds, while for the physical activation, we will involve higher temperature, pressure, and also gasification. But the problem with this two kind of activation is for chemical activation, for example, it will produce more hazardous chemical waste. And also for the physical activation, it will use a higher energy compared with the previous one. So how can we how can we compensate the disadvantage of these two methods? This one, the conventional method, how can we compensate? So we try to use low temperature solvothermal method. Of course, you can also refer this method as a hydrothermal method, but for me, I prefer to use this terminology, solvothermal method. So we can generally describe this for water-based solvent, also for organic solvent. So in here, we try to use this kind of solvothermal method using the typical autoclave, very simple autoclave, to activate the carbonized sample and get more porous structure in the carbon sample. So in here, we hope this kind of activation will lead to the lower energy utilization, and also more eco-friendly, because the chemical waste here can be used again and again, not only for one time utilization. So in here we carbonize the sample at first, carbonize the coffee waste sample, and then we get the carbon. After that, we try to study the feasibility of low temperature activation using this kind of autoclave solvothermal method. First, we compare when we put the carbon sample. We put the carbon sample in the solvent, immerse the carbon in the solvent, and also we put the carbon sample here up above the solvent here. So in here, the carbon sample will be boiled within the solvent, while in here the carbon sample will be steamed in the solvent vapor, and we put this one in the oven and heat treat it at 200 degrees C for 24 hours. So this is the experimental method. The carbon waste will be carbonized here using simple heating carbonization. At first, we tried these three temperatures, and after that, we characterize the infrared properties of the carbonized sample, and also after that, we conduct the solvothermal activation using this parameter. Temperature is about 200 degrees C, time 24 hours, and we use potassium hydroxide 0.5 molar for preliminary experiment, and after that we compare using a higher molarity solvent. And after that, the obtained activated the sample, the treated carbon sample, will be printed here in the aluminum and copper foil, and after that we make a circle, the carbon circle here, and we cut, and we will transfer it into the coin cell here, and making the cathode of carbon, and also the anode of lithium titanate in here, and we assemble it in lithium ion capacitor assembling, and after that we perform the cyclic voltammetry examination, and also charge discharge examination, and also another examination, and also we calculate the specific capacitance to determine which treatment is better compared to other treatment. So this is the characteristic of the carbonized coffee waste. At first, we try to examine the thermogravmetry profile of the coffee waste. In here, we can see for the for the treatment below 500 degrees C, there is still some small peak here. So we can know in here below 500 degrees C, there is still some functional group in the sample. So we cannot use the temperature below 500 degrees C because some of the remaining volatile will keep remain in the sample. So we have to carbonize the sample above 500 degrees C. But if we compare the FTIR spectra of coffee waste and the carbonized sample at 500, 600, and 700 degrees C, we can see here for the sample carbonized at 500, 600, and 700 degrees C, there is no significant difference. So we can just use the lowest temperature, which is 500 degrees C for carbonization. And we also after carbonization, we conduct the treatment using solvothermal in autoclave, and after that we compare the morphology of the carbon sample. Here we can see the morphology of the carbonized sample at 500 degrees C. The texture morphology is already obtained, but after we treat it in the solvothermal method, the pore has been opened. Not similar with when we compare with the carbonized sample. But if we compare with the so we also make some variation the amount of
4 minutes
solvent. Okay. Excuse me. Excuse me.
Yes,
4 minutes, please.
Okay. So we made some variation.
You have 4 minutes, yes.
Okay, we made some variation regarding the volume of the solvent. This is 30% and 40% and 50%. From here, from this three variation, we can see here when we use 40% volume, the pore development is better than for other treatment. So after that, we also compare using different solvent and also different setup. This is the solvothermal and this is the steam solvothermal. Solvothermal is when the carbon sample is immersed in the solvent, while the steam solvothermal is when we put the carbon sample above the solvent. So we just put some steam and vapor to modify the pore structure of the carbon sample. So we can see here, if we use a steam solvothermal method, we can see here the pore development of the carbon sample, and also we can avoid the collapse of the pore structure of the carbon sample. We can see here, if we use steam, the pore structure is still better compared with the solvothermal method. And also we conduct the measurement of the nitrogen phase absorption, and we can see here using the 40% volume of the solvent, we can get the highest phase absorption profile. And we also compared the morphology comparison between the solvothermal and steam solvothermal using two kind of solvent, which is potassium hydroxide and zinc chloride. K is potassium hydroxide, S1 is solvothermal, conventional solvothermal, while Z is zinc chloride, and S2 is steam solvothermal. So we can see here the more porous profile of KS2 sample it should facilitate more lithium plus ion insertion from the anode. So we consider this kind of carbon sample is better than that of other sample. So we also measure the Nyquist plot of lithium ion capacitor cell, and we can see here for the sample with a steam sulfothermal method, it will generate a smaller resistivity compared with the sulfothermal method. And this is the voltammogram of porous carbon based full cell LIC. We can see here the voltammogram has a pseudo rectangular irregular curve. So this kind of shape indicates the capacitive nature of a capacitor. And this is also this data demonstrate the charge discharge profile of carbon-based full cell LIC. So we can here for the sample KS2, the charging profile is longer than other sample, and it represents the best result compared with other sample. So we also calculate the specific capacitance. So we found that the KS2 cell possesses the highest specific capacitance at a scan rate of 5 millivolt per second. So for the conclusion, this is some of my our result. So we can conclude in this research, sulfothermal and steam sulfothermal method can be used to engineer the morphological features of carbon samples at relatively low temperature, only 200 degrees C. And depending on the parameters, we could introduce a more porous morphology than that of the sulfothermal method. So, and also depending on the parameters, we could possibly generate a milder activation method, milder activation mode, which we hope can avoid the collapse of the porous structure in the carbon sample. Okay, thank you for your attention and enjoy your coffee.
Thank you, Dr. Wahyu, for your nice presentation. Ladies and gentlemen, you can ask questions in the chat box for Dr. Wahyu to answer later. So for the next speaker, our last speaker is Dr. Andri Hardiansyah. He is our Research Center for Physics junior researcher. Dr. Andrei Harianza has a bachelor and master degree from Bandung Institute of Technology, ITB, and he graduated his doctoral degree from National Taiwan University of Science and Technology, or NTUST, Taipei, Taiwan Republic of China, which his research on development of liposomes for control release via pH and magnetic stimuli triggering mechanisms. For Dr. Andri Hardiansyah, time is yours.
Okay, thank you, Mr. Andi, for introduce myself. Okay, good afternoon, everyone. Dr.
You
Rico,
have 15 minutes.
Dr. Maruyama. Okay, and all of the presenters today, thank you for inviting me to join this webinar to share our current research related to the development of graphene-based materials. My name is Andrei Hardiansyah from Research Group of Low Dimensional Functional Materials, Research Center for Physics. And before I share my current research, please let me introduce our research group. We have 5 principal investigators. There's me, and then Dr. Rika Yudianti working on carbon nanotube, and then Dr. Hamza Fauzi working on spintronics, and then Fredina Destyorini, Miss Fredina working on graphitic structures, and Ms. Yuyun Irmawati also working on carbon-based materials and also doping, atomic doping for carbon-based materials. And here is the outline for my presentation today. First, I would like to introduce the graphene-based materials and its potential application. And today I would like to share about the graphene-based materials for electrochemicals and also some in non-electrochemical application. And we would like to see the future prospect of these materials. And before we start to the experimental details, I would like to start my presentation with the brief history about the graphene oxide and graphene-based materials. Actually, graphene-based materials or graphene oxide, the research have been conducted a long time ago, about 1885, since Brody start to oxidize the graphite materials. And the research continue with the development of graphene oxide synthesis. And the research related to the graphene-based materials have been accelerated with the advancing structural characterization like XRD and NMR. And also the very phenomenal experimentalists conducted by the Game and Novoselov related to the graphene materials trigger the speed of research in graphene-based materials theoretically and experimentally. And here is the basic structures of the graphene-based material. Actually, the structures of graphene-based material consists of carbon, and in which the graphene-based graphene material consists of two-dimensional layer of well-arranged carbon structure, which makes the graphene has a very unique and superlative properties. Another type of the graphene-based derivative, namely graphene oxide. In graphene oxide, we see that not only carbon as an element, but also oxygen-based functional group attached on the surface of the graphene. And also we can change the structures of the graphene oxide into the reduced graphene oxide by several techniques. And here is the schematic illustration how we change the structures of the graphite into the another type of the graphene-based derivative like graphite oxide, graphene oxide, or reduced graphene oxide. And here is some brief introduction about the synthesis and how we fabricate the graphene-based material. Actually, there's a chemical vapor deposition and micromechanical cleavage and chemicals methods like Hammer's method or Tour methods. And the last is chemical method by using Hammer's or Tour method is one of the most favorite method that experimentalists conducted in order to prepare the graphene oxide and their derivatives. And also we can see the price and then the quality of the process. And then of course we still can use the low price of the process. However, maybe we can adjust the quality and see what kind of the application that's suitable for. And here is some selected application of graphene oxide and reduced graphene oxide. And I believe that I still have so many limitations in our research, and hope by this webinar I can get some suggestion for improvement for our research in the future. And here's the research map. I conducted the graphene synthesis since 2012. And then until now, we still prepare the graphene oxide, and then we try to see the potential application of the graphene-based materials, especially as functional materials. And in the first section, I would like to share some selected application in respect with electrochemical application. And we have tried to use this kind of graphene-based material as an anode for lithium-ion battery. And actually, we try to use tofu waste in order to prepare the graphite, and then we convert it into the graphene-based materials and then apply for the anode materials. And we see the comparison between one and another structures of the carbons, and see that graphene-based material has promising properties that we can utilize for the anodes materials in lithium-ion battery. And the second one, we try to prepare the composite consists of graphene oxide and some polymers, and I believe also some cerium nanoparticles in order to prepare the composite of graphene oxide. And this project is a collaboration project with the Kumamoto University through the IROS programs. And we prepare the graphene oxide by using the vacuum filtration, and then we check the proton number to see whether the our composite has a good proton conductivity or not. And based on this, we still doing some research related to the proton number of the composite of graphene oxide. However, it's quite promising if we use for some electrochemical application, like for fuel cells or maybe for battery, because graphene oxide has a good proton conductivity due to the abundance of oxygen functional group attached on the surface of the graphene oxide. And the second section about the application of the graphene oxide and reduced graphene oxide in another application. So maybe I will give some quick review about the absorption spiration, and then some application in source detection of DNA and also the bacteria. And we prepare the graphene oxide the same by using the chemicals methods, and then we try to make the composite with the inorganic nanoparticle, which is the ferro-oxide, and then here's some TEM figures, and then we try to check with the antibacterial properties by using the AURES, and then we see that the concentration of the graphene oxide could have effect on the capturing of the bacteria, and we believe that this kind of material could apply for the absorption in bacteria or the metal ions. And the second one about the still in the development of the source nanobiotechnology, we prepare the same with graphene oxide, and then reduce graphene oxide, and then try to composite it with gold nanoparticles, and then because gold nanoparticle has a hotspot effect during the spectroscopy, the Raman spectroscopy, we can get the enhancement of the Raman signal, especially for the adenine and then the aureus. Of course, the concentration of the nanocomposite has the very high influence in the detection of this adenine or the bacteria. And still the same for the source application. We try to put the ferro-oxide in the graphene oxide and then the gold nanoparticles, and we can get the magnetic properties and also the source properties by using this kind of nanocomposite. And then here's some TEM images of the nanocomposite. And then probably the last application that we might use graphene oxide and their derivative may be the photocatalyst and then quantum dot fiber and tissue engineering based on graphene oxide. And in the second section, we try to use the ferro-oxide and then gold nanoparticles. And then here we use titanium dioxide in NATS phase in order to make some photocatalyst effect on our nanocomposite. And it works as a photocatalyst, and we can we use rhodamine as a model for the pollutants. And another one interesting application is quantum dot application. However, it's still under investigation. We try to reduce the size of the graphene oxide into the dot structures or a very small size of graphene oxide by using the laser ablation. And we have checked some spectroscopy characterization. However, maybe we still have to investigate the photoluminescent characteristic of the graphene quantum dots. And some morphology or structures that we can develop using the graphene oxide is the fibers structures or fiber morphology. Herein, I use the wet spinning in order to prepare the microfiber textile by using the graphene oxide, and it's quite interesting because there has some porous morphology of the fibers, and then of course there's some mechanical properties we can get, and then probably it can be used for like a sensing application in the future. And the last for my presentation in application of the graphene oxide, we use it for the hydrogel based on the graphene oxide, and we try to mix between the graphene oxide and some hydrophilic polymers and make it like hydrogels by using very easy techniques. We have tried to check the antibacterial of the graphene oxide hydrogels by using the aureus. And this is almost the end of my presentation today. I would like highlight our work, mainly verified that the potential application of graphene-based materials as supporter materials with metal oxide nanoparticles, metal nanoparticles, and or polymeric materials. And it also highlights more generally the potential application of graphene-based materials in the field of nanocomposites, molecular or environmental detection, electrical or sensing application, or biomaterials. And that's all for my sharing and presentation today. Thank you for your attention, and thank you for your hearing in my presentation.
Thank you, Dr. Andri Hardiansyah. Ladies and gentlemen, it's time for the questions and answer. I think we have already like 3 to 4 questions here. First one is from Muhammad Pasha. I think it's to everyone. What is the best carbon can be? Maybe to Dr. Wahyu or Dr. Andri, if you want to answer. What is the best thing carbon can be?
Is for my, sorry, what the question, Mr. Andy?
What is the best thing carbon can be? For Muhammad Pasang. I think maybe that questions can be also asked to Dr. Jun later on. But
can I answer the question?
Yes, Dr.
Okay. I think the best carbon. I think carbon. Many thing in our daily life made from carbon. So I think carbon can be everything. So I don't know what is the specific intention of this question, but for me, there is many kind of potential of the carbon. So we can explore many things from the carbon material, and today we know about the carbon nanotube, graphene, and many kind of functional carbon material. But in the future, maybe we can get many more advanced material than we can get now. So I think carbon can be everything in our daily life, because all of our life consists of carbon. I think maybe yes. Maybe
In organics, yes.
Yes, yes, yes.
Okay, thank you, Dr. Wahyu. I think there is also two questions to Dr. Wahyu Bambang.
Okay.
One is from Putri to Dr. Wahyu. Based on your presentations, you have investigated lithium carbon with your carbon material by using various types of electrolytes like acidic, base, and salt. Which one is suitable for carbon-based material due to each higher characteristic in lithium carbon applications? And could you explain how was it's going on? And also about the power density on your research. Thank you. That's the Putri. And the second question is from Dr. Jun to Dr. Bambang. Have you measured Raman or XRD to check carbon phase?
Okay.
You have two questions, Dr. Wahyu.
Okay, thank you. For Miss Putri, actually, to be clear, I was not using acidic or base or salt electrolytes in our lithium ion capacitor cell. So we use lithium hexafluorophosphate electrolyte for potassium hydroxide and also ammonium hydroxide and also zinc chloride. We use it. We just use this kind of solvent. That's my answer.
Okay, thank you, Dr. Wahyu. There are also two questions to Dr. Andri. First is from Dr. Jun. What is the effect of Fa3O4? I think it's regarding maybe in your composites in the battery applications, maybe. And the second one is from Dr. Yuliati Herbani to Dr. Andri Hardiansyah. What is the fundamental difference between the GO and RGO in terms of functional group and its properties? And what can we transform RGO into pure graphene with a simple method?
Okay. Thank you for the question from Dr. Maruyama. And what is the effect of iron oxide? In my case, in my research, actually, we try to use the ferro-oxide nanoparticle as one of the most common magnetic-based nanoparticles in order to give some magnetic effect in our nanocomposite. Because we try to use it for the separation of the bacteria or the iron, in the metal ion, metal ions. So we try to use the magnetic nanoparticles so we can easy to separate it from the system. That's my answer for your question. So simply to give some magnetic properties in our nanocomposite, and also it's quite easy to synthesize the Fa3O4, and for some case the Fa3O4 quite biocompatible with the biological system. And for the Dr. Yuliati, I would like to answer the question. And what is the fundamental difference between graphene oxide and reduced graphene oxide in terms of functional group? Yeah, in my opinion, it's the most fundamental difference between the graphene oxide and reduced graphene oxide is on the oxygen functionality on the surface of the graphene oxide and then the reduced graphene oxide. Well, actually the research and the analysis of this graphene oxide and reduced graphene oxide is also quite difficult, since we cannot predict, I think, exactly what kind of oxygen functional group on the surface of the graphene oxide or reduced graphene oxide. However, we can check it by using maybe X-ray photoelectron spectroscopy or XPS. And I also believe that the oxygen functional group on the GO is higher than the RGO. So because some oxygen functional group on RGO have been removed during the reduction process, and we know that a lot of reduction process we can use in order to remove the oxygen functional group on the surface of the graphene oxide. And the second question is, can we transform RGO into pure graphene? In my opinion, pure graphene is two-dimensional material that consists only carbon-based carbon element, and with the very range structures. And we know that in reduced graphene oxide, some of the structures have been defect by because some reduction techniques. And by using simple method, I think we cannot get a very pure graphene without any maybe oxygen functionality on the carbon based structure. So and I also still think that maybe if we want to synthesize pure graphene, maybe the best method still CVD or micromechanical cleavage, as Professor Game and Novosel conducted their experiments. So the fundamental difference, of course, the oxygen functional group, and we can check the oxygen functional group, and then can be transformed into pure graphene. Maybe it cannot until 100% into pure graphene. Maybe still consists of the defect in their structures, and we can also investigate the structures by using maybe Raman spectroscopy also. Hope that answer the.
Thank you, Dr. Andri, for your comprehensive answer for all our participants' questions. Unfortunately, we have very limited times, and for all participants who still have questions, can ask directly to all the speakers by contacting them privately, or if you don't have email for our speakers, you can ask or email to our center, our Physics Research Center. We have an official email address in our website, so you can ask questions if you still have questions need to be answered. And ladies and gentlemen, we finally arrived to the end of this webinar. On behalf of Research Center for Physics, Indonesian Institute of Sciences, we would like to thank you once again to all respectable speakers. Special gratitude to our invited speakers, Dr. Jun Maruyama from Osaka Research Institute of Industrial Science and Technology, ORIS, Japan. We wish you always in good health and great success in your research. We would like also say thank you to all participants who attended this event and actively participating in this webinar by asking questions. We hope this webinar brings a mutual benefit for all of us, extend our knowledge, and strengthen our research collaborations. At last, we would like to apologize for any inconvenience matters during this webinar. Thank you. See you again in our next colloquium or webinar sessions, and have a good evening.
So see you again soon.
Thank you
very much.
Thank you.
Thank you very
See you
much.
again, Dr. Maruyama.
Thank you very much.
Thank you.
Andri? Okay, thank you.